Okay, welcome to Haemostasis. What I've got on screen is the very, very rudimentary structure of a blood vessel. So let's just go through what the different layers are called, because it's the kind of thing you should remember, really. So the first thing we've got, they're all called tunica something. So this is the outside layer. Outside is external, so therefore the tunica externa. Tunica is a middle layer. And this is internal. Tunica interna. And then inside here then, this little guy here. It's the basement membrane. Why am I telling you about this when I'm talking about clotting? Because the whole point of all of this is to keep blood flowing through this. Okay? To keep blood flowing through that. So, two things that we need to think about, so as I go through my notes to make sure that I'm not talking utter crap, is to remind ourselves how blood flows. So, blood, if we take this here blood vessel and we just draw a very, very, very rudimentary version of it like this. So, got our endothelial cells all along here. Our endothelium like that. And then, because I've drawn that in pink, I'll change colour and I'll do blood in blue, right? Okay, so blood will flow like that, like an arrowhead shape. That's how it's going to move. So what this means to us is that we can kind of replace that very bulbous looking arrowhead with something a little bit simpler to get the point of what I'm trying to make across to you. This friction on blood, that means the stuff, the layer of blood, because blood will flow in layers, the layer of blood that is closest to the endothelium is going to flow slightly slower than the next layer in, and the next layer in, and the next layer, and so on, and so on, until we get to the layer that's flowing in the middle. So we end up with something like that. Okay? So that's called parabolic flow. Cool. Parabolic flow. Why is that important? Well, we've got to get our blood to wherever it is that it's got to go. So the size of this vessel is going to be important. So what we don't want is a clot that's going to be kind of like this size, like that. Almost gave myself a monocle then, didn't I? A clot that's like that size, because then that blood can't flow through that bit and the whole thing has got to try and flow like this. So what that tells you is that even if we can maintain parabolic flow, our flow is going to be less so than if we had a wider vessel. This is governed by something called Poiseuille, S-E-U-I-L-L-E, Poiseuille's law. Now, what Poiseuille's law tells us is this. Delta P equals 8 times the viscosity of the fluid, length of the vessel, divided by pi times r to the power of 4. Now, the important thing, the really important thing about this equation is this. Okay? Later on in your scientific careers, you'll find that the dynamic viscosity of the fluid is quite important. For right now, what's really important is, well, two things. One, let's get rid of that. Number one is the fact that we're talking about r to the 4. And what that means is we're talking about this. It's talking about the radius of the vessel. And it's to the power of 4. So what that actually means, if I just clear this off so that you can actually get a look at my ugly mug when I'm talking to you. What it means, because we got r to the 4, is that if we take this r and we half it, as we've very cleverly done with this thing here. So we've got r, or we've got 1/2 r. Okay? It means that if Poiseuille's law tells us that if you double the diameter of a vessel, because it's r to the 4, you increase flow 16-fold. Conversely, if we half the diameter, then we decrease flow by 16-fold. Now we want to make sure that we can get as much flow going through these vessels as possible. Because something really quite interesting happens is that if we've got an adequate pressure differential, oh look at that delta P, if we've got an adequate pressure differential from one side of the vessel to the other, then what can actually happen is if we put that clot in the way and we half the radius of the vessel, or half the diameter of the vessel, whatever you prefer to talk about, then what we can end up getting is a buildup of pressure, and then this laminar flow stops, and we end up getting turbulent flow. And that's not good either. So, the point of haemostasis, the really important point of haemostasis, is that it actually keeps blood from clotting. And in the next snippet, we'll talk about the difference between a blood vessel that is in a normal setting versus one that is in a setting that is set up for clotting.